In this series of videos, I take a knowledge question, for example one of the past prescribed TOK essay titles, and give two examples in response to it. One of these examples is appropriate for a TOK essay, and the other example looks deceptively TOK-ish, but is not actually appropriate. Your job is to tell the difference and identify which of these two examples is good and which one is bad. At the end of the video, I tell you what I think about it and explain my reasoning. The first pilot episode seemed to receive some positive response, check it out in the links below the video, so we keep going. So without further hesitation, let's grab a question from one of the past prescribed essay titles and look at two different examples that might be used in response to that question, one good example and one not so good. Understanding something requires being able to answer what-if questions about it. To what extent do you agree with this statement? This is a prescribed essay title from November 2020 exam session. I will pick natural sciences as my area of knowledge, and both of my examples will be linked to natural sciences. Example 1. Albert Einstein's famous thought experiments. When he was just 16 years old, Einstein, in his very first thought experiment, imagined that he was traveling on a beam of light. As you know, and as was known in physics at that time, light is an electromagnetic wave traveling through space, an electromagnetic oscillation propagating with large speed over large distances, much like a regular wave propagates through water, although of course much faster. The speed of light is denoted by the letter c. Experiments have determined the exact speed of light in a vacuum to be 299,792,458 meters per second. Imagine how fast that is, by the way. 300,000 kilometers covered in 1 second. The circumference of the Earth is approximately 40,000 kilometers, which means that in just 1 second a beam of light can travel around the Earth 7.5 times. But we all know that speed is relative to a frame of reference. So if I'm standing in a field and there's a train moving past me and you are on that train, I will see you moving at a certain speed because you are in fact moving relative to me. But if I'm on the same train sitting next to you, then you will appear motionless because we're now both on the same train, and so relative to me, you're not moving. So what would happen, said Einstein, if I travel alongside a beam of light with the same velocity? Relative to me, the beam of light then has to be motionless, much like when you and I are sitting on the same train, moving in the same direction, and we're not moving relative to each other. Einstein tried to imagine that. What would a motionless beam of light be? What would it look like? As he said in his paper, this would have to be an electromagnetic field at rest, though spatially oscillating. Einstein thought that this was very weird. He wrote, "There's no such thing." On the one hand, this was not imaginable in the context of the theory of electromagnetism. An electromagnetic field at rest, though spatially oscillating, could not be described by the existing equations. On the other hand, there is stuff in the universe moving in all sorts of directions relative to us all the time. For example, stars moving quickly away from us and stars moving quickly towards us, and all these stars emit light that we see. So if the speed of light actually depended on the speed of the star that's emitting it relative to us, then we should see frozen light beams around us, at least sometimes, but this is something we never witnessed. So Einstein believed that there's no such thing. This led him eventually to claim that the speed of light is the same in all reference frames. If you think about it, this claim is actually really bizarre, and one can wonder how on earth young Einstein would even suggest such a weird thing. What does it mean that the speed of light is the same in every reference frame? It means that the speed of light appears to be constant, no matter if you're moving or not. So if you're standing on the surface of the Earth and observing a beam of light whooshing past you, the speed of this beam of light will appear to be c. But if you hop on a train that is moving in the same direction as this beam of light, its speed will still be c, even relative to you. and if you hop on a beam of light that is traveling in the same direction alongside with that first beam of light, the first beam of light will not appear frozen. It will still in fact move relative to you with the same speed c. This is a bizarre idea which eventually got experimentally supported and became one of the foundational principles of Einstein's relativity. And it all started with a thought experiment. So how does this example link to the essay title? Understanding something requires being able to answer what-if questions about it. A thought experiment essentially is a form of what-if question. Einstein asked, what will happen if I travel on a beam of light? What will I see? And this allowed him to understand something, the nature of light, better than his contemporary physicists understood it. This suggests that asking what-if questions is really important for understanding. Without asking such questions, you are doomed to think about the problem in a limited context. Consider only the things that are accessible to your everyday perception. Thinking about possible scenarios allows you to explore various aspects of the problem and look at it from various unexpected angles, which in the long run encourages you to investigate previously unnoticed nuances and gain important insights. This is a little bit like saying that imagination is important in the discovery of knowledge, because imagination allows you to create experiments that cannot be created in real life, thought experiments. No one can possibly travel on a beam of light, so a what-if thought experiment really seems to be the only option here to investigate this. And of course, conducting such what-if thought experiments is helpful because it gives you more data and more aspects of the phenomenon to think about. Was it a good example or a bad example? Make up your mind. In the meantime, I will move over to my second example. Example 2. As a matter of fact, this will also be about Einstein's thought experiments, just to make it possible to contrast the two examples more clearly against each other. Einstein's claim that the speed of light is the same in all reference frames is bizarre, so we can have a look at other viewpoints existing at that time to see if there was an explanation less bizarre than Einstein's. If there's a less bizarre explanation and it works, we should take that explanation. There were two such theories. The first one, called the emission theory of light, suggested that the speed of light depends on the speed of the emitting device. But if this theory is right, then we should be able to see frozen beams of light. The problem was not just that the idea of a frozen beam of light seemed strange. Being strange is okay. What matters here is that this idea was inconsistent with physics, with the theory of electromagnetism of that time. So it created a contradiction. In the emission theory, or if the emission theory of light is true, then frozen beams of light should exist. But frozen beams of light cannot exist according to the theory of electromagnetism. So at least one of these theories, either the emission theory of light or the theory of electromagnetism, must be incorrect. They cannot both be correct. Einstein's thought experiment helped highlight this contradiction. The second theory was the ether theory of light, very influential at the time, and Einstein came up with another thought experiment to put this theory to a test. This theory suggests that the universe is filled with a hypothetical substance called the luminiferous ether, and this substance is invisible and almost undetectable, and that this substance is at rest, and that it serves as a special absolute reference frame. When you and I are sitting next to each other on a train, we're not moving relative to each other, but we are still moving in an absolute sense because we're both moving relative to the luminiferous ether. The ether theory suggests that the speed of light is fixed relative to this special reference frame. It may appear faster or slower to someone else depending on their motion, but it always has the same fixed speed c relative to the luminiferous ether. Einstein had another thought experiment that allowed him to realize that this approach does not work either, because it creates a contradiction when you try to detect what exactly the state of rest of the luminiferous ether is. The thought experiment is called the magnet and the conductor. Situation 1. Imagine a magnet which is at rest in the luminiferous ether. According to the theory of electromagnetism, a magnet at rest creates a magnetic field around itself, but it does not create an electric field. So if you place a conductor around it, like a wire arranged in a loop, the magnet will not push the electrons within the wire because no electric field is being generated, so there will be no electric current in the conductor. In situation 1, both the magnet and the conductor are at rest in the ether. Situation 2. Now imagine the conductor is at rest in the luminiferous ether and the magnet is moving through it. According to the theory of electromagnetism, a moving magnet generates both a magnetic field and an electric field. The electric field will cause electrons in the wire to move, so we will observe an electric current in the conductor generated because the magnet moves through the luminiferous ether, and this motion creates an induced electric field. In this situation, the conductor is at rest in the luminiferous ether and the magnet is moving. Situation 3. Imagine the magnet is somehow attached to the conductor, so they are moving through the ether together. Electromagnetic theory dictates that in this case there will be two opposite forces. First, the moving magnet will create an induced electric field that will push the electrons in the conductor, creating electric current. Second, the conductor moving through the electric field will also create a flow of electricity, but in the opposite direction. The theory predicts that these two forces will cancel each other out, and the net result will be no electric current in the conductor. In situation 3, both the magnet and the conductor are moving through ether, and there is no electric current in the conductor. Look at situation 1 and situation 3. In situation 1, we do not observe any electric current in the conductor, so we can conclude that the magnet and the conductor are at rest in the luminiferous ether. But in situation 3, we also don't observe any electricity in the conductor, so we might come to the same conclusion. Although this time we know that both the magnet and the conductor are actually not at rest in the luminiferous ether. Conclusion: there is no way for us to know whether the magnet and the conductor are in motion or not, relative to the luminiferous ether. In other words, even if this absolute frame of reference exists, then it is impossible for us to detect it. Einstein's thought experiment revealed that ether, if it exists, will always remain undetectable. Then Einstein asked, what is the point in believing in the existence of something that is impossible to detect? We should reject ether, as well as the idea that there exists something that is at rest in some absolute sense, reject the idea that there is an absolute frame of reference. As a result of this, he proposed that the speed of light is the same in every reference frame. This became known as the light postulate and became one of the foundational principles of Einstein's relativity. So this second example is also about Einstein's thought experiment, but it links to the question in a slightly different way. In my first example, I said Einstein used his imagination and came up with these thought experiments which allowed him to look at the problem from various unexpected angles. This helped him think out of the box and eventually helped him create the relativity theory. In this example, it was Einstein who asked the what-if questions, and it was Einstein who understood something. In this second example, however, the focus was not on Einstein, but on theories. The question was, what happens if we travel on a beam of light, or what happens if a magnet and a conductor travel together through luminiferous ether? Different theories suggested answers to these questions, and it was revealed that some of these answers create contradictions. Some theories were not able to answer the what-if question without creating a contradiction. For that reason, Einstein suggested that we must reject those theories. Is this example better than the first one? Which of the two examples in this video did I intend as the good one, and which one is the bad example? Give it a thought and pause the video if necessary, and I will let you know what I think in 5 seconds. Okay, this is actually not easy because the difference between the two examples may not be that obvious. partly because they were both actually about the same thing, Einstein's thought experiment. But in the way that the examples were used, the way they were linked to the prompt, that made a difference. The first example made a link to personal knowledge, that is, to how Einstein, an individual physicist, acquired knowledge. It talked about how thought experiments were helpful to Einstein because they helped him look at problems from different angles. It is Einstein who asked the what-if questions, and it is his understanding that developed as a result of that, personal knowledge. But the focus of the TOK essay is supposed to be on areas of knowledge, and areas of knowledge is something that we know collectively as human beings. The focus here should be not on the individual physicist Einstein, but on natural sciences. Understanding here should not refer to Einstein's understanding, but to our shared understanding within natural sciences. If you look more closely at the second example, you will see that this example is not about Einstein, but about scientific theories. The thought experiments, what-if questions, were the hypothetical scenarios, and the different theories, such as luminiferous ether, relativity, electromagnetism, or the emission theory of light, were applied to these scenarios. Some theories could not be applied successfully, which outlined limitations of such theories. This means that the understanding provided by such theories is not sufficient. So, indeed, understanding something in natural sciences requires being able to answer what-if questions about it. In natural sciences, we have a theory and we test it, and we accept it as long as it is consistent with data, but some tests cannot be conducted because they're not practically possible. For example, we cannot travel as fast as light does, and we cannot detect the luminiferous ether, so we cannot really test some of the theories directly. In these cases, what-if questions, thought experiments and hypothetical scenarios can be helpful. A good theory should be able to answer these questions without contradictions, just like a good theory is supposed to fit experimental evidence without contradictions. I meant the second example as the good one and the first example as the bad one. This is a difference that is very often overlooked by teachers and students. It is not easy to detect this difference sometimes, but it is essential that the focus in the TOK essay remains on areas of knowledge in general, such as natural sciences, and not on anecdotal stories about individuals, even if these individuals happen to be scientists. See you next time.